Right, this is question 11.3 from the FEEG1003 workbook regarding the steady flow energy equation. And question 3 is quite a short and simple question. It helps if you've done a question 11.1 first, because there's certain similarities, especially with regard to including and neglecting kinetic energy components of the steady flow energy equation. So if you haven't already done so, you can watch my video on how to solve question 11.1. But regarding this question, we have an electric hairdryer. So effectively we have a motor, so we're doing mechanical work work on the gas mechanically with the motor. So we're driving the air forward through the hairdryer, a 100-watt motor, and then we have a 600-watt heater. So we're heating the gas as well. So we're given some parameters in the question. We're given the exit diameter, which is 0.03 meters. So converting that. And then we have an inlet and an outlet temperature. Again, convert to Kelvin, unless you're really, really careful and you're happy only using degrees Celsius, whereby you have a difference in temperature. So you're adding or subtracting, for example. So we have an inlet temperature of 18 degrees and outlet of 50 degrees, and no heat loss from the casing. So we can draw a control volume around a hairdryer. So 3 parts of the question. First one, again, the question tells us to assume it's a perfect or an ideal gas. So find the inlet and exit densities. So for that we can just use the equation of state, slightly modified to put it into the form of the steady flow energy equation version, and also the change in specific enthalpy, so energy per unit mass. And then the second part of the question, we're going to assume the kinetic energy is negligible. So we take our steady flow energy equation and chop out everything that we don't need. So the kinetic term and obviously the gravitational term, because we're not given any information on any change in potential energy from the inlet to the outlet. So there will only be the heat term, the enthalpy term. So from that we're asked to calculate the mass flow rate, and then hence the mean velocity at the exit. And then finally, fairly standard way of framing a question, we're asked to recalculate that mass flow rate, take into account now the exit velocity found in B. And the final part is, was it correct to assume in part B that the exit mean velocity is negligible, or should we neglect it? Okay, so that's the basic question. It's quite short. Now we'll go over to the board and quickly run through the solution. Again, with all these videos, if I get anywhere through the question, you think I've given you enough information for you to carry on and complete it. If you haven't already done so, then pause the video, try a bit further, and then obviously click play and use it in such a way so that you're not watching the solutions in their entirety. And also, obviously, always attempt the question first. Never just watch the solution and just think, yeah, I could have done that. It's a common mistake, and quite often when it comes to closed book tests and exams, you'll find that you can't actually do it. So, okay, over to the board. Right, question 11.3. I've drawn a scaled version of the most popular brand of hairdryer. That's a GHD model. And I've written everything in the question that we've already been told. So the inlet and outlet temperatures, the inlet velocity, which is negligible, inlet and outlet pressure, as you can imagine with a hairdryer, is atmospheric. So the first part of the question is asking us to work out the inlet and outlet densities. Now, standard temperature, so when we work out the inlet density, we're expecting it to be around about 1.23 kilograms per meter cubed. And obviously at the outlet, we've got a much higher temperature. So to conserve mass flow, we'd expect the densities to be below that, okay? The temperature is not enormously high, so, around about 1.1 roughly. So again, you can use the numbers and your general knowledge as an engineer as it gets better and better to guesstimate what the answer should be. So if we get a value here of more than 1.23 or more than the inlet density, we know we've gone wrong. Okay, so we can use the equation, property of state equation for an ideal gas. Again, in first semester, we're given this equation. So pressure times the volume equals the mass in kilograms. Remember, this is the big version of the equation. This isn't the chemistry version with moles and everything else. This is kilos of gas, big stuff. R is 287 things, and the temperature. Now we can rearrange this, bring the mass down. Volume divided by mass is actually the reciprocal of the density. So we can rewrite this equation. So pressure divided by density equals R times T. So with that, we can quickly plug in the numbers. We've got everything we need. The inlet pressures are both 1 bar, so 1 times 10 to the 5 Pascal. We've got the temperatures. They obviously need to be in degrees Kelvin for this. So working through, I won't plug in all the numbers now. So inlet, if you put in the numbers, so 1 times 10 to the 5, R 287, and then the temperature in Kelvin, we get the inlet density 1.2 meters cubed, kilograms per meter cubed, and the outlet is 1.08. Okay, the next part of the question is to work out the change in specific enthalpy. So this is per unit mass. So again, from semester 1, from your basic work on fluids, okay, so usually for big H there would be an M in here, but this is specific, so plug in the numbers. So 1004 times, again it's okay to leave those in Celsius now because it's a delta, so one minus the other. So it gives us 32 kilojoules per kilogram. Okay, so that's the change in specific enthalpy. Right, onto the steady flow energy equation. Remember that steady flow energy equation is Q minus W, so heat minus work equals, and then the list of everything out minus the list of everything in, and the list is the mass flow rate times change in, also the specific enthalpy, the kinetic component, and the gravitational potential component. The latter two are both 0 in this case, no kinetic component and no gravitational potential component. Okay, so the steady flow energy equation simplifies to this. Q minus W equals the mass flow rate times the change in enthalpy. We've already worked that out as 32 kilojoules per kilogram. Now plug in the numbers. So there's our heat, 600 watts, and then minus the work, which will be negative because it's work done on the gas. So minus 100. Bringing the 1000 down from the enthalpy. Okay, so this is the expression now where we can find out the mass flow rate. So 600 plus 100, so 700 divided by 1000, 0.7, and then 32 here. Find out the mass flow. So 0.7 divided by 32. So this is the answer in the book, 0.021 kilograms per second. Finally, just come over here to work out the mass flow. This is the equation that I used in solving question 11.1. Again, this is something you can just work out for yourself just by dimensionally balancing either side of the equal sign. So the mass flow rate equals rho times Q, where Q is the volumetric flow rate, so it's the area times the velocity. We need to find velocity. We've got the outlet density, 1.08. We've got the area, because we know the diameter, 0.03 meters. And we've just worked out the mass flow rate. So work this through. So 27.5 meters per second. Again, apologies for everyone that's used to using the letter U for velocity. I've used V because velocity begins with a V. Makes it easy to remember. And it doesn't have units consistent with volume, so I can't get confused. Okay, last part of the question, what if we included that as well? What we have to do is rework this into this equation. So Q minus W equals the mass flow rate, so the change in enthalpy, and then plus this velocity term. So effectively it's delta U, but U at the inlet is 0, so we'll just use the outlet velocity because that's the delta, so U squared over 2. Okay, so you can rework that equation, plug in all the numbers, then you get a new value for mass flow. So our kinetic energy version so 0.0214. So the difference here is what? 2% approximately. So there's a 2% difference if we include the kinetic energy component. Again, proving that if we have a decent mass flow rate and we put enough heat in, the change in the enthalpy of the gas is huge compared to the kinetic energy component. So in this case, our assumption to neglect the outlet kinetic energy was valid. Again, the outlet velocity is quite high, but once you square it and divide it by 2, multiplied by the mass flow, it becomes an incredibly small component of the outlet energy. So nearly all of the outlet energy really is this increase in the enthalpy of the gas. Okay, so that's the end of that question. It's really quite simple. There's plenty of simplifying assumptions given in the question. It strips the whole steady flow energy equation back to just effectively this part here.